So welcome you all in the 21st lecture of embedded system. So in the last lecture we have studied about scheduling algorithm, that is priority driven scheduling algorithms, and we have categorized priority driven scheduling algorithm into two category, that is static scheduling and another was a dynamic scheduling. So in a static scheduling, the scheduling is done at offline. Okay, so it is done at compile time. So we know that the tasks are periodic, and we know the periodicity, execution time, and their deadline. So we just schedule it offline. However, in the dynamic scheduling, the scheduling is done at the runtime. Okay, so this is done at the runtime. So whenever the task is coming, then the scheduler wakes up and it takes a decision, so which task has to run first or second, right? So in the static case, we have studied one algorithm, that is a rate monotonic algorithm, RMA. Okay, so in the rate monotonic algorithm, the scheduling was done based on the rate, and rate means how frequent the task is coming, right? So rate is inversely proportional to the period, right? So period of the task. So whose period is lowest, that will get the highest priority, right? So we are giving priority based on the rate, right? So if period is less means the task is coming frequently, and then we are giving highest priority to that particular task, right? So here we assume that we have only single processor, so this is for this technique is for uniprocessor, and we also assume that there are no shared resources. Okay, there are no shared resources. So that means there is no critical section or the shared resource where the two tasks are accessing the same at the same time, right? So then we have seen that in the last class, that in a rate monotonic algorithm in RMA, when we are assigning the task based on the rate, okay, so we checked in one example that some tasks are not schedulable, right? So we have to do the schedulability check, right? So what is schedulability check? So we have to first check that for the given period and execution time and deadline of a task, the task can be utilized can be scheduled or not, right? And that was done using a schedulability check formula. So that was given based on the utilization, right? So utilization was defined as I equals to 1 to n for all tasks, and that was defined as ei upon pi, where ei is the execution of ith task and pi is the pi is the period of the ith task. That must be that should be less than equal to n times 2 to the power 1 upon n minus 1, right? So this was the condition for the rate monotonic algorithm, right? So here in the rate monotonic algorithm, we have taken an example in which there was no preemption, right? So there was no preemption in the task, right? So today we are going to see dynamic algorithm. Okay, so today we will see the dynamic scheduling. Today we will see the dynamic scheduling, in which the scheduling is done in the real time, right? So scheduling is done in the real time. So in a real time or a run time, basically we call it as run time. So in which the most widely used algorithm is earliest deadline first. Okay, earliest deadline first algorithm. Also there is a minor variation with another algorithm that does also the same thing, in which that is called as it is least laxity. So we have studied what is least laxity. So laxity, we know that suppose the task is executed before the deadline, so whatever the time remains, that is called as laxity. Okay, so that is more or less same that we will study with one of earliest deadline. Okay, so what is earliest deadline? So EDF, if you study the EDF, if you see the EDF, what is actually EDF? So the task will be given priority whose deadline is first. Okay, so in this case the task will be given priority whose deadline is first, right? Also it has to check that whatever the given tasks are there, those tasks are schedulable or not. So for schedulability check, there is a condition. That condition says that your utilization, that is EI upon PI, that should be less than or equal to 1. Okay, so that there was a sufficient condition in the rate monotonic algorithm. Here this condition is necessary and sufficient, both. Necessary and sufficient, both condition, right? So it says that if this condition is satisfied, you can certainly schedule a task. If this is not satisfied, you cannot schedule a task. So this condition is both necessary and sufficient, right? And this schedulability check also follows in the case of least laxity first algo. Okay, it also follows in the least laxity. So now we will take an example for the EDF. Okay, so we will take the same example as we took in the last lecture. So we have basically 3 tasks, T1, T2 and T3. So the period of T1 was 4, 1 was the execution time, and 5 was the period, 2 was the execution time, and 7 was the period, and 2 was the execution time. Okay, so we have seen in the last lecture how did we assign these 3 tasks in a using a rate monotonic algorithm. So today we will see that how these tasks can be assigned using EDF algorithm. So let's say that we have 3 tasks here, so T1, T2 and this is T2, So this is your T1, this is T2, and this is your T3. So this has 4 1, this has 5 2, and third one is having your 7 and 2, right? So I will divide it into blocks. Okay, so this is 1 2 3 4 5 6 7 8, right? So let's say that your first task is coming, so all the 3 tasks are coming. So this is having execution time of 1, so the deadline is 1. So whose deadline is first? Obviously T1 task deadline is first, so this will execute here. Okay, so next time it will come at 4, so after that it will come at 4, right? So this will come at 4, and this T2 task will come at 5, and this will come at 7, right? So if you see now whose deadline is now first, okay, this is anyhow it will come too much later. Now T1 1 is gone already, now T2 has the deadline of 4, right? 1 has already gone, so it has only 4. And what about this? So this has 6, so whose deadline is first? Obviously T2, so T2 will execute here, and it takes 2 unit time, so this will be executed. Now whose deadline is now left? So obviously these 2 are executed, so this will start executing at 3, and now at 4 this was executing, it needs 2 time unit, but here at 4 T1 again came. Okay, so which one will be executed? So T1 came here, so will it be executed? So what is the deadline for this one? So this has a deadline of, because next time the T1 will be coming at 8. Okay, so this has the deadline of 4, and T3 has the deadline. So here if you let me mark it here, so this is 4, this is 5, this is 6, and this is 7, sorry, this is 7, this is at 7, and this is 8 here. Okay, so this is not there. So T3 has a deadline of 3, so this has deadline of 3, and this has deadline of 4. So whose deadline is near? T3 deadline is near, so who will execute? So T3 will execute. Okay, so now if you see here T2 came at this position, so now who will execute? T1 will execute or T2 will execute? So if you see here at this position, the T1 has a deadline of 3, and this is at 5, so after that it is coming at 10. Okay, so this has the deadline of 5, this has a deadline, no, yes, so this has a deadline of 5, this has a deadline of 3. So who will execute? Obviously T1 will execute, so T1 will execute here. Okay, so this is the way all the tasks are assigned, okay, or scheduled. Now let's take another example. Okay, but first we have to check the schedulability condition also. So let me check the schedulability condition also here. So this will be 1 by 4 plus 2 by 5 plus this is 2 by 7. So what is this? So can you find it out? If you do this calculation, is that less than 1 or not? So this is what actually. So 1 by 4 is how much? So if you compute 1 by 4, that comes around 0.25, right? So let me write that also. So 1 by 4 means that is 0.25. 2 by 5 means, so that comes around 0.4. Okay, and last one will be 2 by 7, so that is 2 by 7, so it comes around 0.28. So if you add all three, this comes around 0.93, right? So if you compute it, this comes around 0.93 approximately. So this is 0.93. It is less than 1, so definitely we can schedule all the tasks, right? Now we will take one more example. So let's now I will denote the task T1 and T2. So in the last example we have assumed that your deadline is same as the period, okay, but it may not be the case. So your deadline can be different than a period. So in this case I am denoting any task Ti with a period, the deadline and the execution time. So T1 task period is 3, deadline is also 3, this is 1, and here let's take 6 and 4. So now first we have to check that these tasks are schedulable or not. So how we will check? Just you have to check the formula, schedulability check formula. So what it says that so this will be your 1 by 3, this will be your 2 by 3. So 2 is the 2 by 3 because 4 by 6 is 2 by 3. So if you add it, what will be the total? Total will be 1. So still it is equal to 1. So satisfied. So that means we can execute the task. Now we will execute it. So let's say that this is your T1 and next is your T2. So let me mark it. Okay. So this is, let me mark all the numbers. So now T1 came first. So T1 deadline is nearer, okay, because it has a deadline of period is 3 and deadline is also 3. Deadline is mentioned here. So 3 means first it will be executed. Okay, this is the period. So let me mark here. Okay, now we have a free time. So T2 can execute here. So this is T1, this is your T2. So here T2 can execute. Okay, it needs how many? What is the execution time of T2? Execution time is 4. So 3 it has executed, but now it sees that again T1 came. Now what is the deadline of your T1? So the deadline here of T1 is 3. Okay, and here also the deadline is 3. So you know it can give any priority, any task. Both priorities are equal now, right? Because both deadlines are equal. So it will allow. So it will allow whom to run. Okay, so it will allow. So what is the? Let me write it down. So this is 6, right? So T2 is coming here again. Okay, so let me run T1 here. So what will happen? It needs how many more time minutes? It needs 3 more time minutes. But how much I am getting here, right? So again I will execute this one. Okay, so are we able to execute all or not? We can execute because it has 4. So 4 are done. So now this is also executed, and again you can, again T1 came, so you can execute this one. Okay, the same way this can be executed, right? So this is all about earliest deadline first, right? So in if you talk about least laxity, if you talk about least laxity algorithm, so what it does, who has the least laxity time? So if I go back, you tell me which one is having T1 or T2. So this has a laxity time of 2. Okay, this has a laxity time of 2, and this has a laxity time of how much? So first you check here. So T1 will be executed first. Now it has a laxity time of how much it is? 2, right? 2 is the laxity time here. Now here it is executing. T2 starts executing. It needs 4 units, right? But it did not get here. Why? Because it does not have a laxity here. Again task came, right? So it has to be executed. Is it clear or not? Because this is not even completed. So again it will go to the that least laxity. Okay, so laxity means just you have to check the who is the least one, least laxity. So it is similar to EDF only, just a minor change only, just only they are taking that or they are measuring every time the laxity. Okay, so in the last example we have taken period and deadline equal, but this may not be always the same. Okay, it could be the different also, right? So these algorithms we have studied about these algorithms we have studied about the wherever there was no resource constraint, right? So these algorithms we have studied for there was no resource constraint means no similar tasks are sharing the same resource, right? So the different tasks are not sharing the same resource, so we could able to assign it. Now how will you do the schedulability when two tasks wants the same source? Okay, so for sharing resources, so for sharing resources or shared resources, let me write shared resources. So shared resources means the task T1 and task T2 both wants to access the, let's say it wants to access some particular file. Okay, so both wants to access at the same time, but we cannot allow both tasks to share at the same time. So what will happen? We have to give priority to certain tasks, right? So we have to give priority to certain tasks, right? So the priority can be given to anyone. So this semaphores allows mutual exclusion to assign the shared resources at the different time, right? So let's take an example here. So let's take there are two tasks and the task T1 has higher priority than task T2. Okay, so in this case when T1, let's take an example. So let's see that your T2 is running. So let's see that your T2 is running. So T2 has arrived here. Okay, T1 has not yet arrived. Okay. If T1 has arrived first, obviously it has higher priority, so it will execute first. So now let's assume that your T2 has arrived first, and it since there was no other task, so it starts executing. Okay, now at this point it wants to access a critical section or some file. Okay, so here your T2 came and it wants to access that particular file. So let's call that state as P of S. So now let me denote it with a different symbol. So here I am denoting it as like this. So if it is denoted like this, that means it is normal execution. This is normal execution, and here it is blank one is denoting your shared resources. Okay, shared resource, or let me call it as it is in critical section. It is in critical section. Okay, so now when it is is in critical section, at this time your T1 arrives. Okay, at this time your T1 arrives. Now what will happen? It cannot. So let's say in the middle of that, or at this position, your T1 arrives. So what will happen? It will block your resource to T2, right? So what it will do, it will start executing first. It is a normal execution. Okay, right now it does not want any critical section, right? So at this point we call it as PS. Okay, so now T2 has to wait, right? It cannot access the resource or CPU, so T2 has to wait, and it is a critical section, right? So now your T1 has started executing. Now at this point your T1 wants to access the resource or critical section, not resource, let me name it as critical section. Okay, so here it is an already waiting state, right? So it cannot that access that critical section. So what it has to do, it has to wait. So now it allows your T2 to complete its file sharing part. So it does some more file handling, and at this point it releases that critical section. So let's call that, at this point it releases VS. Okay, so at this point I will call VS, where it releases the critical section. Now it is already released, again it will get the priority. So first it will get the critical section, and then it finishes its normal execution, then only it can start executing the remaining part, right? So in this case, if you see, your T1 is blocked. If T1 is blocked by a low priority task T2, right? So T1 is your high priority than T2, higher priority than T2. So but still your T1 is blocked by a lower priority task, right? So now this is the case of when there are two tasks. Now let's take an example when there are three tasks. What will happen? Okay, so let's take three tasks here. So this is so in this case we assume that your priority of T1 is larger than T2, and the priority of T2 is larger than priority of T3. So now let's start with T3. So now T3 has arrived first, so it will start executing, and it is a normal execution. So let's denote it like this. Now at this particular point, it wants to access the shared or critical section. So here it is, I will call it as PS. So now it is accessing your critical section. Okay, so at this point T2 arrives. Okay, at this point, so this is T2 and this is your T1. This is T1, this is T2, and this is T3. So at this point your T2 arrives. Okay, at this point T2 arrives. So obviously T2 has higher priority, so it has to wait, right? So it has to wait. It is in critical section, but it has to release the sources, okay, so that T2 can execute. Now T2 will execute, and it does not want any critical section. It is just executing in a normal mode. Okay, now at this particular point T1 arrives. Okay, so T1 has highest priority among all three, so T2 will start executing. T1 will start executing. So at this point what happens, T1 wants to access that source or critical section. Okay, so if T1 wants to access that critical section, it sees that critical section is not available, that file is stuck with T3, right? So it can't do anything. So what it has to do, it will go to the next priority task. So who is the next priority task? Next priority task is T2. So T2 will start executing. Okay, so once it finishes its execution, then again because still it is this critical section is still stuck with T3. Okay, so it will go to T3, and then T3 will complete its critical section part, and it will release that critical section file. Okay, now it is released, then obviously it will go to the next priority. So here the T1 can access that critical section, it will complete its rest of the portion. Okay, so now if you see in this case what is happening, in this case you see what is happening in this case, your length of, so this was your length of your critical section. Okay, so PS came here at this position and then it was VS, so here at this position this was released. Now if you see T1 is blocked for this much of duration. Here T1 is blocked by lower priority task, that is even lowest priority task T3, right? So T1 is not able to access that critical section. Okay, and it has highest priority. It has highest priority, and sometimes this blocking time can be more than that critical section. It can be even more than the length of the critical section. So what could the worst case length if I define? So for example, the worst case should be when the one task has entered into the critical section, and immediately after that another task who is having highest priority to that task wants that critical section, so it has to wait until it releases the critical section, right? So the worst case time will be, in this case, if there are 3 tasks, and the worst case time even exceeds your length of the critical section, right? Okay, so if there are 2 tasks, the length of critical section will be, so I will go back to this slide in two cases. So here what is the length of critical section? So here it has entered into the critical section, T2 task, and here let's say that your T1 arrives. Okay, so it has to wait until it completely releases. Okay, so here this is known as the length of the critical section. But in the case of 3 tasks, this is blocking part even exceeding the length of the critical section, right? So if there are more tasks are increasing, there are so many tasks, the waiting time could be even much longer, right? So what is happening in this case, if you see, the T1 was having highest priority, but it became lowest one. Why? Because it was having highest priority, but after that T2 executed, then T3 executed, right? Then only T1 was able to execute. So what is happening in this case? T1 has become even lowest priority. So what happened here? The priorities are inverted. That is called as priority inversion. That is called as priority inversion.